Hello, this is the next video in a playlist that I'm calling Introduction to Probability and Statistics. And we're in chapter 1, part of this playlist that I'm calling Probability. And let's jump to today's topic, which is experiments and events. Now, the term experiment is used in probability theory to describe virtually any process whose outcome is not known in advance with certainty. So here's some example experiments. Flip a coin 3 times. And we may want to estimate the probability of 2 heads being observed. Another example is the number of hits in a Major League Baseball game. We want to estimate the probability that there are more than 6 hits in a game. We could sample 1,000 transistors and examine the number of defective transistors. These are all examples of experiments. Now, the sample space of an experiment is the collection of all possible outcomes of an experiment is called the sample space of the experiment. Now, the collection of outcomes is a set, and each outcome is an element, also called an event, of that sample space. So examples from above, the sample space was from above, is if we flip a coin 3 times, then the sample space S is denoted by this set, and the set contains, 8 elements. The first one is head, 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 meaning we observed a head, then a head, then a head. The next one is a head, head, tail, head, tail, head, and all the way to tail, tail, tail. So this is the sample space, and this is the only possible outcomes. Now, let's define an event from our sample space to be equal to 2 heads observed. So the event A would contain 3 elements: head, head, tail, tail, head, head. Okay. Next, let's look at the number of hits in a Major League Baseball game. So the sample space would be the empty set, right? There's no hits, or H, which is there was 1 hit during a game, or HH or HHH. And I think theoretically it goes to infinity. Now, there may be some Major League Baseball enthusiasts that correct me with that, and I'd love to hear back from that. But let's let the event A equal 6 or more hits observed. So the event A would contain H, 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 6 H's or 7 H's or 8 H's all the way. So that would be the event from the sample space. Now, the next example, sample 1,000 transistors to examine the number of defective transistors. So the sample space here, and I kind of got lazy typing these, but I want to explain it to you. The first one contains 1,000 N's, which stands for not defective, and 0 D's, which would be defective. So now the next element would contain 1 defective and then 99 non-defectives. But then you also have to list all those arrangements. So the first one may be a D and then 99 defectives, and then the next element, that's part of this dot dot dot, would be an N, a D, and then 998 N's, right? It's all possible arrangements of that. Then the next element would be where there's 2 defectives, and then we'd have to list each element, of all the combinations where you could have 2 D's in there, 2 defectives and 998 non-defectives. And then this keeps going until we get to all 1,000 are D's, all 1,000 are defectives. And so that's the sample space. It's all possible outcomes. Now, since sample spaces and events are sets, we need to understand some basic set operations. Okay, so let's assume we have a sample space S, and we have 2 events A and B, and set operations can be visualized with what's called a Venn diagram. Okay, so if the event A represents all elements in event A, which is itself a set. So using a Venn diagram, this is the way we would see it. So S represents the sample space. That's every possible outcome of the experiment. And then we have two events, A and B. And if we just are interested in event A, then we're interested in all the elements that are contained within this set. Now we could look at A complement, or sometimes A, raised to the C, A complement. That means it represents all the elements not in A. And this is how you would represent it in a Venn diagram. It's all the elements not in A. Next, A union B, represented by A, and that's sometimes called a cup, but A union B is this is how you write it. It represents all the elements in A or B. So in a Venn diagram, it would be represented like this, where you shade in the regions A and B. A intersect B, and it's represented by this notation here. And it represents all the elements in A and B. So this is the Venn diagram. So you shade in the area where there's an intersection between A and B. Now the empty set, denoted by this symbol, is called the impossible event. Means it can't happen. The sample space S is called a certain event because one of those elements has to happen. That's what a sample space is. Now B is a subset of A, denoted by this. B is a subset of A if all the elements in B are contained in A, the elements in A. So definition of mutually exclusive events: two events A1 and A2 are mutually exclusive if and only if their intersection produces the empty set. Okay, and we'll look at an example of that. So mutually exclusive events. So let's use the flip a coin 3 times example. And let's let A1 be the event 2 heads are observed. So this is the event A1. Let's let A2 be the event that 1 head is observed. So that's this, right? And the elements of A2 are here. Let the event A3 be 2 or more heads observed. So A3 would be this set. And now note that since A1 intersect A2 is the empty set, then A1 and A2 are mutually exclusive. So note that there's no elements in common between A1 and A2, so it's the empty set. They're not mutually exclusive. So since A1 and A3 is the empty set, A1 and A3 are mutually exclusive. But if we look at A2 intersect A3, we get these 3 elements, right? These 3 elements are common between A2 and A3. So that means A2 and A3 are not mutually exclusive. Okay. Also note that A1 is a subset of A3, right? A1 up here, these 3 elements are contained or part of A3. So A1 is a subset of A3. Now let's do a quick R illustration and call our quits for this video. Now in R, there is some set functions that are part of base R. And let's look at it. So let's flip 3 coins, and this is the sample space. So let's put it in, flip 3 coins dot S. So there's 8 elements, and it's here. Now I want to count the number of H's, or the number of heads in each of these elements. And so that's what this little function here does. And you can dissect it later. As always, I copy and paste all R code to the comments. But that's going to help us create events. So let's let A1 be the event that there are 2 heads. And so this is a way to just grab those 2 events, or the events where there's 2 heads. So HHT, HTH, THH. Let's let A2 be the event that there's 1 head, and so it creates this. A3 is the event that there's more than 2 or more heads. And then intersect is one of the set functions built-in set functions in R. So if we say intersect A2, it produces a character vector of length 0. So it means it's empty. It's the empty set, nothing there. So that tells us that A1 and A2 are mutually exclusive. So that, and mutually exclusive, it means that either one or the other event has to happen. It can't be both. They're mutually exclusive. So if we look at intersect A1 and A3, it produces these three elements, right? Because that's what they have in common. So that says they're not mutually exclusive. So events A1 and A3 could happen at the same time. A2 intersect A3 is the empty set, so they are mutually exclusive. Okay. All right. Well, we're at 10 minutes, and so we'll stop this video. I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.